So let's start to talk about the parameters to represent rotation. So a rigid body, it has how many degree of freedom? DOF stands for degree of freedom. So a rigid body, how many degree of freedom does it have? It has 6, right? It has 6 degree of freedom, 3 translational degree of freedom, which X, Y, Z, and 3 rotational degree of freedom, right? That is the rotation around 3 axes. So now we have a rotation matrix, okay? So my rotation matrix, now I just write down a random rotation matrix. Here I have R11, R12, R13, and R21, R22, and R23, and R31, R32, and R33. Okay, so this rotation matrix these Rij, they're all numbers. Okay, so if we want to achieve a rotation from one frame to the second frame, we can use a rotation. Again, we can use a rotation matrix to represent that. And this rotation matrix, it has 9 elements, of course, because that is a 3 times 3 matrix. So, but actually, these 9 elements, they're not independent. And why is that? It is because when we calculate this rotation matrix, for example, if this is R10, for example, if this is R10, then 0 is my reference. So I'm rotating 0 to a new frame 1, and my frame 0 is my reference. So then, by definition, this should be x1 dot product x0, right? And this R12, that is y1 dot product x0. Because this is x0, y0, z0, x0, y0, z0, and etc. Okay, so then my question is, how many independent variables, how many independent quantities can we use to represent this 9 elements rotation matrix? So then based on the definition of the rotation matrix, which is for example, R10 in this case, and what we know is we can write a lot of equations because we know some of the relationship between these elements. The first is because these are projection, right? Again, based on what we have talked about, they're projections. They're projections, so it means that all of these terms, they have some orthogonal in between, okay? And the first relationship we know is that R1, each row, because that is the x1, y1, and z1, they're projected to x0. So that is one unit vector. Okay, so it means that R11, the first row, consider the first row, the absolute value, adding them together, R12 square plus R13 square equals to 1. Okay, and that is the triangle, right? That is the triangle. And the next one is R21, which is the second row, R21 square plus R22 square plus R23 square equals to 1. And then the third row equals to 1, okay? Still square. And also we know some perpendicular in between, orthogonal in between, right? And we know that these two, this first column and the second column, they're perpendicular. Okay? So it means this vector and this vector, if we do dot product, the dot product, it equals to 0 because the angle between this vector and this vector, that is 0. So then we have R11 times R12 plus R21 plus R22 because we're doing dot product of this vector and this vector, okay? And plus R, okay, read it clearly, this is R21 dot product times because they're all numbers. This is R22 and this is R31, R32 equals to 0 because this is the dot product. This is a calculation of the dot product of this vector and this vector. Okay, and also the first column and the third column, they're orthogonal too, means these two vectors, they're perpendicular to each other. And also the second vector and the third vector, which is the third column, they're also perpendicular to each other, okay? So then we have these two, which is R21 times R12 times R13 plus R22 this term times R23 plus these two, that is R32 times R33 equals to 0. And then we also have this vector and this vector, they're perpendicular, that is also 0. So it means we have this rotation matrix, although they're all numbers, but actually there are six equations, means the 9 elements there, they have some relationship in between. So we have 6 equations. Okay, so now we have 9 elements, we have 6 equations. So it means we only have 3 independent quantities because these 6 equations, it limits the 6, right? The 6 relationship, okay? So it means we have 3 independent quantities in this 9 elements. It means that if we can know 3 independent quantities, we can know the final rotation matrix. We can calculate all these 9 elements. Okay? And then we have a few methods, different type of methods to define these 3 independent quantities. Okay? So what does it mean? It means if we have a rotation matrix R, a arbitrary rotation matrix R, and again this rotation matrix is describing a rotation between 2 frames, and if we have this rotation matrix, we can know 3 independent quantities using different methods, and still we can represent this final rotation action. Okay? And the method 1 is Euler angle. And the second one, which is commonly, is very widely used, that is rho angle. And the third one is axis and angles. That means instead of using 3 angles to describe the rotation, we can define 1 axis and we can use 1 axis plus 1 angle. Okay, so later we're going to talk about it, the calculation of that. That is, in this method, there are 3 independent quantities. Okay, Euler angles. Euler angles provide a way to represent the 3D orientation of an object using a combination of 3 rotations about different axes. What does it mean? So now, for example, I have an effector that is a robotic. So for example, here I have a robotic arm. Okay, here I have a robotic arm. For example, this is a motor. Okay, maybe I have a motor right here. And right here we have a grasper. Okay, that is, for example, this is my robotic arm. Okay, the end effector. And I want to achieve a rotation, a rotation of this end effector. So for example, here we should have a motor too. Okay, here we have a motor, and we're rotating somehow. Okay, for example, this is the center of rotation, and we have two motors. For example, we have two motors, and I want to rotate it to a angle that is, okay, and okay, this is my original position. I called it frame 0 because I want to use a frame to represent this position. And then I rotate to a whatever position, whatever orientation. And this orientation, I name it as frame 1. From frame 0 to frame 1, and they must have, because now we're only talking about rotation. We're not talking about the translation. So it means this thing and this thing, they're at the same spot, okay? They're at the same spot. Means we have a rotation, okay, no matter what is the rotation, okay? And so this is my frame 0, and this is my frame 1. So the Euler angles provide a way that we represent this rotation from 0, from the position, the original position, the original orientation, to the final desired orientation, okay? So, for example, from frame 0 to frame 1. I want to achieve this 3D orientation. And then my question is, what are the actions my robotic grasper need to do? What does my end effector need to do? Okay. So then based on this analysis right here, we know that if we want to understand, we want to achieve this from frame 0 to frame 1, and we know this final rotation matrix that we have 9 elements, R11, blah, 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 and we have this 9 elements. So if we want to know what is the detailed action we are achieving from 0 to 1, we can do 3 rotations in sequence. Okay, so that is the definition of Euler angles. So it means that, okay, so if we can do multiple steps of rotation, and what is the minimum steps? How many steps should we do if we want to achieve a arbitrary rotation from rotation 0 to a new orientation, which is rotation 1? We need 3 steps. We need 3 steps of actions. And these actions means a basic rotation. Okay, and the basic rotation means a rotation around a axis, a rotation around an axis. Okay. So then, okay, so again, if we want to achieve a final rotation means a arbitrary rotation. It is not necessary to rotate around axis, but we want to use rotation around axis to calculate out this final rotation matrix. So we have 1, 2, 3 basic rotation matrix action. Okay, means rotation around. Okay, I'm sorry. Means each of these 3, their basic rotation around axis. Okay. So if we want to achieve a final rotation matrix, we can always use 3 steps of rotation. That is the composition of rotation. We can always use 3 steps to achieve any arbitrary rotation of R. And so then the Euler angle, the interesting thing of Euler angles are that you can use whatever. You can use whatever combination of axes. For example, I can rotate around current X, and then I can rotate around the current Y and the current Z. Or I can do current Z, I rotate around Z first, and then I have the the new orientation, and then I would like to around the current y, and after the second step I would like to rotate around the current z. Okay, and I can also do I run x first, and then I run the current z, for example, and then I rotate the current x. Okay, so you can choose all these different combinations of axes as a sequence. Okay, so in total, how many combinations do we have? We have x, y means y, x, y, x. We can have x, z, x. And if we do y first, that is y, x, y, and y, z, y. And we do z first, z, x, z, and z, y, z. And we can also do x, y, z in a sequence. So for example, I can do x, y, z. And I can do x, z, y. I can do y, x, z, y, z, x, and z, x, y, and z, y, x. Okay, that's all, right? So in total, we have 6 plus 6. So we have many methods to achieve these 3 steps, okay? And we have all these type of 3 steps so that we can have the R. So it means if we want to achieve a final orientation from a original position, which is frame 0, to the final orientation, which is whatever, and although you're not really rotating around any axis, but it can be considered as 3 steps of actions. Each step is a basic rotation around a current axis or a fixed axis. You can consider as either fixed or current. So that is Euler angle. The question is, no matter what is the sequence of your rotation axis, you're gonna have these 3 angles based on the axis you choose as the rotation axis. So these angles are Euler angles. Let's see one example, okay? Although you have 12. Let's just do one example. And I choose ZYZ Euler angle as one example, okay? So we do the rotation, 3 steps of rotation around the current axis, Z, Y, Z. So this is my step 1 because it's rotate around the current axis. So this is my step 1, step 2, and step 3. So it means if I want to achieve this final rotation matrix, which is my final rotation matrix, which is given, that is R11, R12, R13, R21, R22, R23, and R31, R32, R33, and this is my final rotation matrix, and they're all numbers, and I want to know what are my Euler angles so that I can achieve this rotation matrix. And the Euler angles, in this case, we define as ZYZ, so then we can calculate it. Okay, and these are again, in each step, we have a basic rotation matrix and an RZ phi. It means we're rotating around the current Z with the angle phi. So we have this format, right? You can go back to check this format. And then this is Y, so we have this format. And again, that's C, but now we have this angle that is, we call it phi. Okay, this is phi, and I call the thing as phi. Okay, this is phi and this phi. If we want, then we do multiplication. And if we want to do the multiplication of these 3 matrices, first of all, let's calculate these 2 multiplication. And again, we do the row, first row, and the first column, and first row, and the second column. So you will have a new matrix. Okay, after these two, you will have a new 3 times 3 matrix. And this 3 times 3 matrix times the third matrix, and also you're doing the same thing. First row times the first column, first row times the second column, and then after these 9 steps, you will have a new 3 times 3 matrix. Okay, so we're doing 2 steps of matrix multiplication. So finally, this is my term. This is my matrix. Okay, and this matrix is the multiplication result of these 3 matrices. Okay, and this thing, because we assume that this is z, y, z, and it equals to the value of my rotation matrix. Again, these R11, R12, they're all numbers. So that we have 9 equations. We have 9 equations. Then I can calculate it. I can calculate my phi, theta, and phi. So it means that we want to achieve a rotation from the original position to my final position, my original orientation to my final orientation, and then I can use these 3 Euler angles. Okay? And how we do the calculation? How to find the Euler angles? Okay? So how to find these 3 Euler angles? Again, I have this final rotation matrix, and which we just showed it right here, and this thing equals to this matrix. This matrix is calculated by the definition of Euler angle. That is the multiplication of these 3 z, y, z, these 3 steps. And these matrix equals to this final number matrix, so that I have the first term equals to the first term, and the second term equals to the second term, and the third term equals to the third term. So it means I can use 9 equations to calculate these 3 Euler angles, and it is because we have 6 equations already. So we only have 3 independent quantities, which are these 3. Okay? So if we do the calculation for the 9 equations, which are 9 equations with 6 fixed constraint equations, means we are able to calculate these 3 independent quantities based on the R11, R12, based on the 9 elements. Okay? And finally, by solving the equations, I have this thing calculated out, and I have 2 solutions for that. So for Euler angles, we don't need you to do the calculation, because the Euler angles have its own formula. You can just quickly use the formula, and which we will upload to Canvas. Okay, right here. So this is called Euler angle formulas. So you can see that we have 12 combination, right? R, X, Y, Z, and X, Z, Y, and so then based on the axis, you would like to do the sequence of rotation. So you will have these 12 possible rotation sequence you want to do. And this formula shows what are the 12 combination of Euler angles. Okay, so I will just upload this formula sheet. So it means all of these, you don't really need to solve these 9 equations with 6 constraint equations. You just go back to the formula sheet, and then you are able to find the Euler angles for different axes you choose to do the rotation, the sequence of rotation. Okay, so I'd like to stop here.